All right, so we're going to continue in section 2.1. So we're going to start off with a reminder about what a statement is. So a statement is a sentence that is either true or false, but not both. All right, and then we want to talk about inequalities next. So for inequalities, we're going to think of them as being compound statements. So if the statement says x is less than or equal to a, then the statement would be x is less than a or x is equal to a. And then if you see an inequality where, for example, a is less than or equal to x is less than or equal to b, then we view this as an and compound statement, and it says a is less than or equal to x and x is less than or equal to b. So let's look at an example. Let's say I'm looking at 2 is less than or equal to x is less than or equal to 1. What does this mean? This means 2 is less than or equal to x and x is less than or equal to 1. So here we have the and quantifier between these. So you need a number, x, to be a number that's greater than or equal to 2, but also less than or equal to 1. And this statement here, this statement is false no matter the choice of x. For any number you pick, it can't be greater than or equal to 2 and simultaneously less than or equal to 1. All right, so let's look at the next example. Let's suppose x is a real number, and I'm going to let p symbolizes 0 is less than x. Q is going to symbolize x is less than 3. And then finally R is going to symbolize x is equal to 3. And I want you to write the inequality symbolically. So the first inequality we're going to do is x is less than or equal to 3. So we went over this kind of inequality before. This is earlier. This is a compound statement. And so I can write this as x is less than 3 or x equals 3. So here, this first part, x is less than 3, that would be the statement Q. And then I have this or, so you're going to connect them with an or symbol, which we went over last time. And then x equals 3, that's the letter R. So here is my answer symbolically. All right, let's write this next inequality, B. 0 is less than x is less than 3. So this would be a compound statement, and the connector here is going to be and. So you can write this as 0 is less than x and x is less than 3. And again, you're going to kind of dissect it piece by piece. 0 is less than x. That was p. And then there's an and. And then x is less than 3. That was q. And here's the inequality symbolically. All right, let's do one more. So C, 0 is less than x is less than or equal to 3. So again, first expand this out, write it as a compound statement. 0 is less than x, and x is less than or equal to 3. So this first part, 0 is less than x, that's p. And put an and symbol there. Now, this x is less than or equal to 3. We actually did that in part A. So this would be Q and R. And you need a set of parentheses here. All right, so let's talk about truth values next. So recall that we said earlier at the beginning that statements are either true or false, but they can't be both. So what we want to do now, our goal, is that we want to know if compound statements are true. So those are statements with ands or ors or the not symbol, the tilde. So just as a reminder, as I just mentioned it, that the tilde means it is not the case that P. So what we can do is we can use a truth table to figure out if a compound statement is true or false. So we're going to do a simple truth table right now. So let's say we start with P. What are the options for P? P is a statement, so P is either true or false. Those are the only two options. So I'm going to write T for true and F for false. So then if I'm looking at tilde P is like kind of the opposite of P. It's not P. And so if P is true, then tilde P would, or not P, would be false. And if P is false, then tilde P would be true. So they have opposite truth values. So let's look at the statement we looked at earlier. It is hot and sunny. This was a compound statement where we used an and between them. P and Q. Remember, it's denoted P and Q, that little symbol. And we call this the conjunction of P. So let's look at the truth value of P and Q. Well, it depends on the statements P and Q. So So what are the possibilities? Well, P could be true, and then Q has two options. Q is either true, so they're either both true, or P is true and Q is false, or P is false, and then there are two options for Q. Q is either true or they're both false. So there are four options in total. And now let's look at the conjunction P and Q. In order for P and Q to be true, you need both P and Q to be true. So in the first line, P and Q are both true, so the conjunction would be true. But in all the other rows, one of them is false, so the conjunction would be false. What about an or statement? So say P or Q. Remember, we denote this P or Q is called the disjunction of P and Q. So an example of a disjunction would be it is hot or sunny. So let's see when this kind of statement would be true. We're going to use again our truth table. P and Q are our first columns, and we have the same options that we had before, namely true, 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 false, false, true, and false, false. So now let's put in the disjunction right here, P or Q. Now for an or statement to be true, only one of them needs to be true. So in this first row, the disjunction would be true, and the second and the third would be true because one of the two statements is true. But in the very last row, both P and Q are false, so P or Q would be false. Okay, so now we're going to write down another definition. A statement form is an expression made up of statement variables. So usually these are the letters that are usually used are P, Q, and R. And between these, you're going to use logical connectives such as not and an or. Okay, so let's do some truth tables for more complicated compound statements. So let's construct a truth table for the statement form P or Q and not P and Q. So we have two statement variables here, P and Q. So you're going to start your truth table with those columns, P and Q. And we've seen in the past truth tables there are 4 rows here. true, 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 false, false, true, and false, false. And now we're going to work our way up to this statement form right here. So the first thing I see that I need is P or Q. So let's make a column for P or Q. So you just need one of them to be true. This is an or, true, 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 false for an or. And then I also see that I'm going to need P and Q. So let's go ahead and make a column for P and Q. And remember, for an and, the only time you're going to record a true is if both of them are true. So true, and then the rest of the rows are false. And then if I look, I need to negate, the not of the and. So I need to compute not P and Q. And so they're just going to flip, we're going to flip this last column. So the first one was true, so I'm going to write false, and then the rest of them were false, so I'm going to flip it to a true. And now I'm ready to make my final column, which means I'm looking at P or Q and not P and Q. So this is made up of the two pieces, the or from this column, and then the negation here. And your connective here, if you look, your connective is an and. So you're going to compare these two columns, and because there's an and between them, the only time you're going to write down a true, a T, is if they're both true. So I look at the first row, and one's true and one's false, so I'm going to write false. And then in the second and third row, they're both true. And in the last row, one of them is false, so I'm going to record a false. Okay, so let's construct another truth table. Construct a truth table for not P and not Q. So we're going to start. If you might want to take a minute and try this on your own, pause the video. But let's start making our truth table. So again, my only two statement variables are P and Q. So I'm going to go ahead and start my truth table with those columns, and I know I have 4 rows. So I'm going to fill in my rows here. Okay. And then we're going to work our way up to this compound statement. Start pretty easy. Remember, our order of operations says negation comes first. So I see I'm going to need not P. So you're going to take the P column and you're going to flip all the entries. False, false, true, true. I also see that I'm going to need a not Q. So go to that column for Q, and then you're going to flip all the entries. False, true, false, true. Okay, and then if I look here, I need to combine the last two pieces with the connector and. So again, you're going to look, this time we're going to look now at our last two columns here, here and here. And we're using an and between them. So the only time you write down a T is if they're both true. So I see I have a false, 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 and true. The only time they're both true is in the very last row. All right, so how do I do a truth table when I have 3 statement variables? So for example, let's say I want to construct a truth table for the statement form. It's going to be P and Q or not R. So here I'm going to have 3 statement variables, P, Q, R. And I'm going to run through all my possibilities. So P could be true, Q could be true, and then R could be true or it could be false. P could be true, Q could be false, and then there are 2 options for R, true and false. And those are all of the cases when P is true. So now let's run through the ones where P is false, false, and then they're both true, false, true, false, 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 true, false, false, false. So now when I have 3 statement variables, you're going to have 8 rows in your truth table. So we're going to go back to our truth table here, our compound statement here, statement form, and we're going to build it up in pieces. Okay, so let's look here. The first thing I see I need is P and Q. So that's going to be my first column now, P and Q. They both P and Q need to be true to write down a true. So look at your first 2 columns. Anytime you have 2 T's, you're going to write down T. So true, true, false, false, and then the rest of them are all going to be false. Okay, and then I also see that I need the negation, not R. Not R. So I'm going to make a column for not R. And all you're going to do is take your column for R and you're going to flip all the entries. So false, true, false, true, false, true, false, true. Okay. And now we can make our final column, which is P and Q or not R. So you're going to use these last 2 columns here, here, and here, and they're connected with an OR. So you only need one of them to be true to write down T. So true, true, false, true, false, true, false, true. And that's how you do a truth table with 3 statement variables. All right, so now that we know how to construct 2 truth tables, I want to talk about logical equivalence. So let's say I tell you that 6 is greater than 2. And then someone else comes along and says 2 is less than 6. Really, we've just said the same thing. So these 2 statements, they essentially say the same thing. Okay, so another example here. Let's say we compare P and Q to Q and P. So for example, it is hot and sunny, or it's sunny and hot. And let's look at the truth table here for these statements. We're going to stick them together. So remember, now we're back to just 2 statement variables. So I only have 4 rows. Okay. And let's look at P and Q. Remember, you need them both to be true to write down a T. And now let's construct Q and P. So you're going to look at this one first and then this one. Again, they both have to be true to record a true. So what happened in these last 2 columns? Let's compare these last 2 columns. Hopefully you can see that they're identical. And this is exactly what it means to be logically equivalent. So the definition, you can say that 2 statement forms are called logically equivalent if and only if they have identical truth values for each possible substitution of statements for their statement variables. So no matter what I plug in for those variables, P and Q, they would have identical truth values. So the way we denote logically equivalent, if we have 2 statements here, let's say P and Q, the way we denote it is P is equivalent to Q. So there's 3 little lines instead of just an equal sign here. So let's look at another example. Let's look at this truth table. Let's do P. Just look at one statement variable, P. So there's only going to be true rows, true, false. And let's look at not P. You flip them. And now let's take not P. So here you flip this last column, take that last column and flip the entries. And what do you see? You see that the first and last column are the same. Here and here, these 2 columns are the same. And so what does that tell us? Well, these 2 are logically equivalent. So you can write P is logically equivalent to not P. Okay. Let's look at one more. Let's look at show that the statement forms not P and Q, and not P and not Q are not logically equivalent. So I want to show that two things are not logically equivalent. We're going to construct the truth table for these two. We're going to put it together in one truth table. So let's do P and Q. Those are my only two statement variables. So we're going to have 4 columns. False, true, and false, false. So I need not P. I also need not Q. So you're going to take the P column, flip the entries. I'm going to take the Q column, flip the entries. I also see that I'm going to need P and Q. So that's true, false, false, false. So now I'm going to negate that last column to get me my first statement form. Flip all the entries. And then my other statement form over here is not P and not Q, so I'm going to take an and between this third column and this fourth column. And there's an and between them, so you need 2 T's to write down a T. So it's going to be false, 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 true. And if you look across these last 2 columns here, these are not the same. And I'll circle row 2, they're not the same, and row 3, they're not the same. So one way you can show two statements are not logically equivalent is to show that when you make the truth tables, their columns are not identical. Okay? You have another option on how you show two statements. Statement forms are not logically equivalent. And so that other way to show these statements, we'll just say these are not logically equivalent. Is to find statements where one is true and the other is false. So we need to make choices for P and Q where they have different truth values. So let's go with P being the statement. Let's say P is 0 is less than 1, and we're going to use the variable Q here. We're going to replace it with 1 is less than 0. So let's look at the first statement form, not P and Q. This says it is not the case that 0 is less than 1 and 1 is less than 0. this statement is going to be true because 0 can't be less than 1 and 1 less than true. Both of those things, these two things, are not both true. So this and statement would be false. Now let's look at not P and not Q. This would say 0 is not less than 1 and 1 is not less than 0. So if I look at each piece, this part is false. 0 is less than 1. 1 is not less than 0. That's true. So one of them is false and one of them's true, but there's an and between them. And so this statement is false. So we have two different truth values here. The first statement form had a true truth value, and then the second one had a false truth value. So they're not logically equivalent. Okay, so what I want us to look at now is one more truth table. Let's look at P, Q. Again, we have 2, so we're going to have 4 rows. All right. And let's look at not P again, not Q, P and Q. So flip all the entries in P, flip all the entries of Q, and now take an and between P and Q. So look at the first two columns, an and, true, false, false, false. And so what I want us to compare are the columns not P and Q. So you're going to take this last column right here and you're going to flip all the entries, false, true, true, true. And let's look at not P or not Q. So this is almost what we looked at before, but we had an and between, and now we're going to have an or. So you're going to look at these two columns right here, and then put an or between them. So you only need one T to write down a T. False, true, true, true. And look at these last two columns. They're identical. Or the same. So that tells me these two things are logically equivalent. So when you negate, we can now write the negation of P and Q. It's equivalent to not P or not Q. And I'm not going to show it, but you could also show that not P or Q is logically equivalent to not P and not Q. So this tells you how to negate an and an or statement. These are actually together are called Demorgan's Law. And it tells you when you negate an and, you negate each piece, but then the and becomes an or. When you negate an or, you negate each piece, but then the or becomes an and. So you flip the sign in the middle as well. This makes it really easy to then negate statements. So let's look at an inequality. Let's use Demorgan's law. Laws to write the negation of -1 is less than x is less than or equal to 4. So first, you should probably write this as a compound statement. -1 is less than x, and x is less than or equal to 4. So using Demorgan's law, the negation would be what? Well, you're going to negate each piece. So let's start with this first part. The opposite of that would be -1 is greater than or equal to x. You're going to negate this last piece. X is greater than 4. And then for this and, it flips and becomes an or. So if you were doing this graphically, you want all the numbers less than or equal to -1, but greater than 4. Okay, so it's the negation of all the numbers of our inequality that we started off with. Okay, so we're going to talk about what a tautology is now. This is a statement form that is always true. Regardless of the truth values of the individual statements. Substituted for its variables. So a tautology, if you looked at its truth table, its column would have all t's in it. So you can probably guess what a contradiction would be. A contradiction is a statement form that is always false. Again, regardless of the truth values of the statements substituted for the variables. So let's show something as a tautology. P or not P is a tautology. So I need to construct the truth table. There's one statement variable P, so I'm only going to have 2 rows in my truth table, true, false, and then I need not P, so flip the entries. And now the last column will be P or not P. You just need a single T to write down a T here. So again, this column only had T's in it, so this shows that this statement form is a tautology. You could do something similar to show P and not P is a contradiction. So P, not P P and not P. So again, you have two rows, true, false, flip them, false, true, and then it's an and, so I need two T's to get a T. So both of them are going to be false. So here, this part tells me that this is a contradiction. So usually, if you have something that's a tautology, we use the letter T for tautology, and then in its truth table, its column would only have T's in it. However many rows of T's you need. And then a contradiction, we use the letter C. And so if you have a contradiction in your truth table, the column will only contain F's, however many F's your truth table needs. Okay. So the very last thing I want to talk about is there's another way to show logical equivalence without using truth tables at all. And so what you use are some known facts. So this is theorem 2.1.1 in your book of logical equivalences. Just for completeness sake, I'm going to write all of them right here. This first one are the commutative laws. So they tell you that P and Q is equivalent to Q and P. And the same thing with an or. P or Q is equivalent to Q or P. Okay. The second one is the Associative Law, which tells you P and Q and R. This is equivalent to P and Q and R. And then you have a similar statement but with ors. This is logically equivalent to P or Q or R. Okay. Commutative law, associative law. So the third one is going to be the distributive law. So it tells you how to distribute P and Q or R. This is equivalent to P and Q, or P and R, P or Q and R. This is logically equivalent to P or Q and P or R. You have some identity laws. Those tell you P and a tautology would be equivalent to P. P or a contradiction would be equivalent to P. You have negation laws. They tell you P or not P. That's a tautology. P and not P is a contradiction. We saw those earlier. Number 6, you have the double negation law, which we saw earlier as well. Not P is equivalent to P. Seven, idempotent laws, which tell you that P and P is equivalent to P. P or P is equivalent to P. 8 universal bound laws. P or T is equivalent to T. P and C is equivalent to C. Demorgan's laws, which we went over those. Those say not P and Q is equivalent to not P or not Q. Not P or Q is equivalent to not P and not Q. We only got 2 more, bear with me. Just putting these in here for completion. Absorption laws. P or P and Q, that's equivalent to P. P and P or Q, that's equivalent to P. And then the last one, these are the negations of T and C. The negation of T is C, and the negation of C is T. And again, if you think about it in terms of truth tables, this last one makes sense. You're flipping all the columns in T, which are all true, and then they become all false, and vice versa. Okay, so how can we use these rules here to help us show that statements are logically equivalent? So we've got one last example. Use theorem 2.1.1 to verify not P and Q and P or Q is equivalent to P. So what you're going to do is you're going to start with one side, and in this case I would start with the left-hand side, and you're going to essentially use your rules to help you simplify. So the first thing you're going to do for this first part, use Demorgan's law. So Demorgan's law says you negate each piece, so this is now going to say not P. And you flip your signs, it's going to become an or, not Q, and P or Q. Okay, so we just used, should write down which rule you used, Demorgan's law. And then here we have not P, that's the double negative law. So this is equivalent to P or not Q and P or Q using the double negative law. And so now, if you notice, they kind of, these two have the same P or there. So we can use the distributive law and write this as P or not Q and Q. And then for this, we can use the commutative law. So rewrite this as flip the two, Q and not Q. Well then for this, it's in our parentheses still, we can use the negation law, which tells us that's a contradiction. And then the last thing you're going to use is the identity law to tell you that that's the same thing as P. And that's what we were trying to work our way down to, is P. Okay, so we just showed that these two statement forms are logically equivalent, just using our laws and our rules from theorem 2.1.1.